Extreme values. First, we're ready to talk about an absolute maximum. It's also called a global maximum. Official definition: if C is a number in the domain D of a function f, then f of C is the absolute maximum value of f on D if the function value at C is greater than or equal to all other function values for all x in the domain. So mathematically, this is simply saying if we have a function and the absolute maximum occurs at a C value such that the function value at C is greater than or equal to all other function values for this function. And so we can see right here we have an absolute maximum, and similarly we've got an absolute minimum or a global minimum if C is a number in the domain D of the function f, and then f of C is an absolute minimum value of the function if the function value at C is less than or equal to all other function values for all x in the domain. So the number C is where the absolute minimum occurs, and the absolute minimum is the function value at C. You can see graphically here this is the lowest value the function ever obtains. It occurs at C and the function value is f of C. All other function values are greater than or equal to this value. Let's go ahead and look at this one, and I actually should have show that this clearly ends here. As we're looking at this, we're looking for an absolute minimum, the lowest that this function ever goes. This would be found at A, and it is f of A because the lowest function value this function ever obtains is f of A. Now looking for an absolute maximum, we can see that occurs when the x is D. The highest the function ever goes, the largest function value, is f of D. So that occurs at D. But let's look at B. If we're looking at B, this is actually the largest the function ever gets right around this area, in a neighborhood around. So if I looked at function values from say 0 to somewhere here between B and C, and I looked at the function values there, all function values are less than or equal to this value. So this is called a local maximum, local being in a neighborhood or somewhere near you. There's also local minimums. If we looked at C, anywhere in an interval around C or a neighborhood around C, all function values are greater than or equal to the function value at C. So this one's a local minimum. And looking, we also see that we have another local minimum right over here at E. Now I wanted to mention this endpoint because this kind of differs by book and by definition, and so it depends on how they define a local max and a local min, whether you include endpoints or not. If they are defined as we're going to define them here, it will not include endpoints. Some books do include endpoints in the local max and min, so it's important to see how it's officially presented and defined. So here is our local extrema. Extrema is the plural of extreme, so both max and minimum extremes. Suppose I is an interval on which f is defined and C is an interior point of the interval. If f of C is greater than or equal to f of x for all x in some open interval containing C, then f of C is a local maximum. Now notice this said some open interval containing C. So to have an open interval containing C, if we were looking here and here C, I would need to be able to get some values on either side of C. Because it is defined this way, an endpoint would not qualify for local extrema, because if the function value is not defined past this point, I can't get an open interval around it that would contain C. And similarly, if f of C is less than or equal to all function values for some x in an open interval containing C, then f of C is called a local minimum. Because they are using this open interval definition, endpoints are not counted. Looking at this particular graph, we have that there is an absolute minimum right here because no smaller value of this function occurs anywhere. This says it's also a local minimum. According to this book's definition, this would not be true. Now this came out of a different book, and as I just was emphasizing to you, it depends on how they have made their definitions. In this one, you have to be able to get an interval around A such that this function value is less than or equal to all function values around A, and I can't get an interval because this function is not defined for anything to the left of A. Okay, this one is a local maximum. I can get an interval around here so that this is the largest function value anywhere nearby. Here we have a local minimum. Same idea, there's no smaller function value locally or near this. I can get an open interval around this such that this is the smallest function value. This one is an absolute maximum because it is the largest the whole function gets, but it is also a local maximum because I can get an interval around it where it's the largest. So it's an absolute and a local. And this one is incorrect for our definition because if we look at this value here, I cannot get an open interval around B. It is the lowest it goes from this left-hand side, but it doesn't exist, so I can't get any values on the right-hand side. And this is not the lowest the function ever goes because it goes lower other places, so that's nothing. So let's find the absolute maximum and absolute minimum values of f of x equals x squared on the interval from -2 to 1. It's often useful to look at graphs, and we know that this is just a parabola, but we're only taking the piece between -2 and 1. So here is our graph, and if we're looking for absolute maximum, the highest it ever goes would occur right here on the endpoint. And so the highest it goes would occur when c equals -2, and the absolute maximum is the function value then at -2. So that's the highest it goes there, and so of course we know that is 4. Now looking for the absolute minimum, we're looking for the lowest this ever goes, and that occurs right here. So the absolute minimum would occur when c equals 0, and it is the function value at 0, which is 0. All absolute and local extrema for the function f of x equals x cubed. Again, I like to think of the graph, and we know this from our library of functions. It looks like this and continues on. So if we're looking for absolute extrema, there are not any because this function continues towards infinity, and it also goes down and continues on the left hand side towards -infinity, and so there is no absolute value that you can say this value the function never goes above it, or this value the function never goes below it. Okay, looking for local extrema, if we're looking, is there a place where we've got it is the lowest locally or the highest locally? And there actually is not ever any of that either, because this is always an increasing function. So this has none, no local or absolute extrema. This is an always increasing function, so there's not an area where there's a low point or a high point. Okay, if we're considering f of x equals sine x, and we look at this graph looking for absolute, actually we are just looking for a function value that the function never goes above. It's always greater than or equal to any other function value, and that actually occurs in several places. It occurs every time we have this pi over 2 at c equals pi over 2, and then we could put plus 2k pi, the absolute maximum would occur, and the absolute maximum is the function value there, which is 1. So even though it happens multiple times, it exists. It just happens in several places. So to have an absolute maximum, it is the function value that the function does not go above. Every function value is less than or equal to this value. It happens to equal the value at -3 pi halves, at pi halves, at 5 pi halves. They all equal 1, so there are multiple places where the absolute maximum occurs, but the absolute maximum is 1. Similarly, the absolute minimum is going to be -1, and -1 is going to occur at 3 pi halves and multiples of 2 pi added or subtracted from that. So the absolute minimum is -1, and it occurs several times. Now, both of these absolute extrema are also local, because in an area around this I could get an interval where that was the highest point, and I could do that on every one of these. And I could also do the same thing for the absolute minimums. They're also local minimums because I could get an open interval around them such that on this interval they are the smallest function value. So okay, we then have the extreme value theorem. If f is continuous on a closed interval from a to b, then f obtains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in the closed interval. Okay, so this is just saying we are taking a function and we are looking at it on a closed interval. So we are not looking from negative infinity to infinity. We have a closed interval, endpoints a and b. Let's look at this graphically so we can kind of make some sense of essentially what it said. So here we have this closed interval from a to b, and this is saying that somewhere on this closed interval there exists a c such that the function obtains its absolute maximum, and there exists a d such that the function obtains its absolute minimum. Now it doesn't say that they have to be in between, it's on the closed interval, so they could be on the endpoints or in between, and that is why having a closed interval and having endpoints guarantee that there will be these absolute extremes. Now the extreme value theorem is difficult to prove with the tools that we have at this level, and so we're just going to look graphically so we can sort of, get at least an intuitive sense of why that would be true. So here is another example of a possibility. Here is C that's in between A and B where it achieves its absolute maximum. And then here at D, which happens to equal an endpoint, it achieves its absolute minimum. So you can see because we have these endpoints and have this function that would have to have a maximum value somewhere and a minimum value somewhere. Here is another example, and in this particular example it attains a maximum actually in two places. It's okay to have a tie. We can have several places like we saw in the sine graph, but bottom line, there is a maximum value, a value that no other function value goes above. It's okay if another function value equals it, so hence we got a tie here at C1 and C2, and then here is our absolute minimum that occurs at D. Now looking at this one, if we're looking on the interval, closed interval from 0 to 2, does not ever attain an absolute maximum, because you can see as I get closer and closer and closer to 3 here, because there's an open circle at 3, I've got a problem, because you tell me an absolute maximum value and maybe you say 2.999 and I can get closer. I can say 2.9999 and you can get closer and I could get closer, and so this one does not attain an absolute maximum. So what failed if we had the extreme value theorem? Very important to have the word continuous function in there. This will not necessarily be true if it's not a continuous function, and that's what we're seeing here. We don't have a continuous function and it does not attain an absolute maximum on this closed interval. Okay, another example, if we're looking from 0 to 2 here, it doesn't have an absolute minimum, and it also doesn't have an absolute maximum, because here as we're getting closer and closer to this, because it doesn't equal the endpoint, whatever value you gave me, I could get something a little smaller. And on this particular end, it doesn't have a maximum because this is heading towards infinity. So whatever value someone says is the maximum, you can get a function value higher than that. So the other piece of the extreme value theorem that's extremely important to guarantee an absolute max and absolute min is the closed interval. So extreme value theorem, in order to guarantee that you have an absolute max or an absolute min on a interval, it needs to be a continuous function and it needs to be a closed interval.